Hi, everybody. My name is Sean Pierce. I'm presenting in E106, 107 on defending against malicious application compatibility shims. That's what it says. So I'm having some interesting problems with this. So, just a little bit about me. My name is Sean Pierce. I'm a threat emulation engineer for iSight Partners. There's my Twitter, my GitHub, and this website, sdb.tools, where I've posted all the code, all the demonstrations for today. And if you want to email me, sdb@securesean.com. It's where you can shoot me an email. I don't know what else to say. I have a CISSP and a few other certs, and I like taking things apart. Background is malware reverse engineering. So, as a disclaimer, I'm not a developer. My code isn't the cleanest, not the most efficient. I'm not an iSight representative. However, I love who I work for. I can't say enough good things about them. The people there are great and super smart and humble, and everyone speaks like 3 or 4 languages. And I just love the people I work with. And if you want to learn more about them, they do cyber threat intelligence. I think they're actually the only ones that do it like really, really well. And like I said, if you want to learn more about them, there's their website. But continuing on to the talk. So when a lot of people ask me what my talk is about, I really don't know what to say. It's like, oh, in Windows, there's these shims, there's these things that manipulate processes. And people are like, oh, okay, that's kind of cool. But it's actually like really tactically powerful. It's incredible how much power these things have, but we need to get a little vocabulary first. And I want to go into like a little bit of history of application compatibility. And Microsoft, I think, is the main reason why they're so dominant in the marketplace. It's because they put so much effort and energy and time and money into application compatibility to make sure everything is backwards compatible. And a lot of it is from third parties. They have really dumb bugs. They do things the wrong way, and they don't obey any kind of standards or anything. And Microsoft bends over backwards to make sure things work. As an example, the original SimCity was written for Windows 3.1, and it had a free after use vulnerability, or a free after use bug. There was just like no vulnerability. I'm just used to saying that. And whenever we would call the free function on some memory, it would still continue to use it. And that's kind of terrible, because if the operating system took that memory back, the program would crash. And in Windows 95, they actually like made the memory manager super efficient and would actually take the memory back and use it for other concurrent processes, of which there are many more. And so when people installed SimCity on Windows 95, they saw that it was crashing all the time. Of course, if you have like program XYZ and you install it on your new operating system with the same old computer, and you notice one's going really slow and the other is crashing all the time, and the third one is just barely working sometimes, the font is a little off, you're going to blame the operating system and take it back and get a refund. But in actuality, it's like Microsoft is doing really well and these other third parties are doing really bad. Sometimes it's actually Microsoft's fault. It's kind of like a first-party bug instead of a third-party bug, and developers come to rely on certain features or lack thereof in the operating system. For example, there's something called a synchronous buffer commit. Now, when you like call a write function and you write some data to a file, you think your data is now on the hard drive, right? Well, that's not actually what happens. Operating systems actually store that data in a buffer and then write that data to the hard drive whenever it's a good time for the operating system. It does it efficiently. But sometimes you need to guarantee that your data is on the disk. You need to guarantee that your file is in a good state, like for a database program or for an accounting program or some kind of transactional thing. Well, so a lot of operating systems have this kind of synchronous buffer commit where it's like, I guarantee that this data is written to disk before your program continues on. And this is great for people who like wrote databases for Windows 3.1 and earlier operating systems. And they really liked this feature because it was so fast. Like they were writing bytes left and right and just flushing the buffer to disk, and there was almost no performance impact. It's fantastic. Until Windows 95 rolled around and it was really slow, like crazy slow. And people were wondering why their database program was running 10 times slower on Windows 95 than it was on Windows 3.1. Well, it's because Microsoft didn't actually like make it work on Windows 3.1. It didn't do anything. And so like developers were like taking a byte, flushing it to disk, taking another byte, flushing it to disk, taking another byte, flushing it to disk, thinking that it was just getting written to the file. And there was really no impact. So what was Microsoft to do? Disable that function. And then they bury the option for that function, that functionality deep within the performance parameters and some checkboxes and some other things. So sometimes it's Microsoft's fault, but usually it's like a third-party developer's fault. And a lot of applications aren't coded very well to work on all the architectures. And so a lot of what Windows does to manipulate a process is done for like a 32-bit program running on a 64-bit system. And I'm sure most of you are aware of this stuff, and I'm really sorry I'm heaping a lot more pain on something that's already pretty painful for a lot of system administrators. So just to get some vocabulary down, I'm going to be referencing three main things. One is a fix, one is a mode, and one is a shim. Now, a fix is kind of like a singular little manipulation of the program. So make sure it runs as administrator every time it executes. Or if it has to run and use the display, make sure it's only in 256 color or something like that, some little thing. There's also called a mode, where they kind of bundle a bunch of fixes together. So when they say like compatibility mode for Windows XP SP3, that's a whole bunch of fixes that they've bundled together, and that's now a mode or a layer. So when I say I want to run something in a Windows 95 compatibility mode, that's really just a bunch of little fixes that they've like put together. Really nifty. So when I say shim, I'm actually talking about some code that gets injected into a process. All right, this is going to sound pretty good here in a minute. You'll see. Now, when a parent process calls create process or nt create process or any one of many process creation functions, it checks to see if that child needs to be shimmed. And if it is, it kind of provides this undocumented application or _ app compat undocumented environment variable to the child. And the child gets that, and it does the same sort of check to make sure it needs to be shimmed, usually. And if it does need to be manipulated, Windows will automatically inject this bit of code that hooks something called the import address table. Now, typically an application will make this import address table, and it's a list of all the functions it's going to call, it's going to require from the operating system, from Windows, the Windows API proper. So when a shim is injected, it's actually sitting in between the import address table and Windows. So when I say shim, I'm talking about this chunk of code. And some of you may be thinking, okay, that's hooking. Like, you're just hooking the import address table. That's not such a big deal. But Microsoft has actually gone to a lot of trouble to do this, and they do it really well. So if you tried to call, if your program application tried to call a function dynamically, like get proc address, that function's hooked as well, and Microsoft, like the shim engine, automatically like takes that and manipulates it. If you try to call an application, or if you try to access a function by going to the DLL, manually loading it into memory, and then walking its export address table, the shim engine will take that too. So Microsoft has actually gone to a lot of trouble to make sure no application can get around this shim. So it's a very, very powerful rootkit framework, or compatibility framework, whatever. So we need to think about, okay, whenever a shim, a fix is installed, what is it actually doing? So there's one fix that I have that manipulates the registry. And when I looked to see exactly what it was doing, it was actually hooking like dozens and dozens of various registry API calls. But we'll get to that in a minute. So shims aren't just used for third-party bugs, although that is the majority of how they're used, but they're also used for kind of this first-party extension of various other functionalities. So Emmet, the Enhanced Mitigation Experience Toolkit, that's implemented through shims. So if you say, I want to lock down this process, I want to lock down this web app or web server or whatever, you can say, hey, Emmet, make sure ALSR is enforced, make sure DEP is on, make sure this is on, and that's done through Shims. So Microsoft is actually putting in some code into that process space and manipulating the input and output and making exploitation harder. How many of you know what fix-it patches are? Thank you for raising your hand. I'm gonna throw you a t-shirt. Is that okay? All right. Thank you for participating. Seriously, I've seen times with other people's talks, I'm just like, oh yeah! And everyone's super quiet and I'm just like, oh. Anyways, so if there is an exploit that's actively being used out in the wild and Microsoft is working on it and it's just like, okay, we have a patch, it's going to be released patch Tuesday in 20 days or something like that. And you're a business, you're just like, WTF, I can't wait that long, give it to me now. You can just go to Microsoft's site and get a fix-it patch. So it's a little single installable thing where you download it, double click it, and you are now patched. Well, if you actually download one of those files and crack it open, it's actually a shim, it's an SDB file. When I say, sorry, I didn't mention this before, and here, SDB files are shim database files. That's where these fix and mode configurations are stored. Oh. So if you crack that open, you'll find an SDB file, a shim database file, and it actually just applies this really cool fix. And that fix manipulates, Internet Explorer is usually the target fixes for these fix-it patches. And it'll say, okay, whenever you boot up, patch these bytes. So shims can actually not only apply fixes and modes and do other lots of cool stuff, the main thing that's I think is super dangerous is it can apply hot fixes to anything in that process's memory. So a lot of times, Microsoft will make these shims that'll apply a little fix. It's like a little jump around for this or a little add an extra reference to that. So it prevents exploitation. Sometimes there's a memory leak, sometimes it'll cause the process to crash, but there will be no exploitation. It's kind of like a quick and dirty patch until patch Tuesday comes around and a much better suitable thing is released. Microsoft also uses shims occasionally for other random stuff, like in Windows Vista, when it first came out, they used shims to kind of monitor the user and see how they were using Vista as a kind of weird way to collect data. But I haven't seen them do that before or since. So as a first demonstration, I'm a very hands-on person. I'm going to show you that it's super easy to create a shim. They're widely supported by every Windows operating system out there, and they can do some really devious things. I'm going to show you how to create an SDB file and how to install it. And I'm going to do it with this free tool that Microsoft provides called the Application Administrator, or the Application Compatibility Administrator. I'll frequently refer to this whole ecosystem as the Application Compatibility Toolkit, or the ACT. So I'm just going to pull up the 32-bit version to make a 32-bit shim. I'm going to target PuTTY. So hopefully, let's see if I can just pause it. Yes, I can. Awesome. Oh, wait, it's not resuming. Anytime now? Okay, so here I'm going to specify the PuTTY program, and I'll tell you why in just a minute. And the first screen I see, whoa, buddy, why'd you stop? I guess I'm going to fast forward a little. So the first screen you're going to see is after I select PuTTY and hit next, is a, God, what the? Yeah, seriously. Okay, I got a funny story. Oh, no, that's not it. I'm just going to do it manually. Wow, runtime error. Awesome. Speaking of compatibility, Oh, Jesus, come on. Okay. I'll speed up a little bit. So right before this screen, we get a list of modes right here. And we can select, hey, do you want to disable, this thing, or you want to disable that thing, or you want to enable fade, or usually a lot of graphics things. And the next screen, we can see 367 fixes. And a lot of these fixes are pretty cool, like log API, or API logger, BIOS read, or block run as interactive user, copy HKey local user, run as administrator. Some fun stuff, admittedly, but I'll tell you what's even more fun. If you go to the application compatibility administrator, if I'm just looking at the location with this shortcut. I'm just going to cd change directory to it on the command line. And if you provide a parameter to it that's undocumented of /x, this is the compatadmin.exe. And if you just do that /x and go through your little process again, you just right click, create a new application fix. I'm going to specify putty again because I love putty. You're going to have to select it and just go past the modes. We now have 808 fixes. So I'm going to choose my favorite one called inject DLL, which, as you can imagine, it might just inject any DLL into any process we want, regardless of privileges. So let me show you my hello world DLL here that's just in C:/users. I just provide that as a parameter to this fix. I can just hit next. And remember when I said that we needed to choose putty, we needed to go to it, and I'll tell you why in a minute. This is why. Because Microsoft's trying to help you out. They're just like, okay, we know that there's probably one random version of your program that's broken and needs this fix. So here's all the things you can trigger off of. Not just putty.exe as in a file name, but you can also go off of size. You can go off of bin product version. You can go off of file description, of author, of company name, of original file name, all these things. But I usually unselect all of them because I want to target everything named putty.exe. So I could just right click and hit install right there and it would install it. But I'm going to do it manually and show you why in a minute. So first I need to specify a database name and a file to save it to. So I'm going to just name both the file and the database the same thing just to keep things simple and just save it on the desktop. And it'll be like putty underscore DLL underscore inject. Sorry if the font is a bit small. So I just saved it on the desktop there. And I'm going to navigate to that SDB file with my command prompt. Now, if I were to right-click and hit install in the GUI, it would just pop up a CMD, a shell, really quick and run a command, and that's it. And so I'm going to run the command manually, and that's SDB inst putty DLL inject.sdb, and it says installation of putty successful, and it says mix new folder there. It says installed SDBs. And our shim is now right in there. We can delete the original file, and I'll tell you why in a minute. And now, when we run putty, that's the DLL. That's our code being injected. Woo! Cool. So I'm going to run past this dumb video built into PowerPoint. So again, what just happened? I showed you just an undocumented trick to get a lot more fixes. And a lot of these fixes aren't super secret or incredible. They're just kind of funny because they target usually very specific things like Acrobat 5 or Macromedia Dreamweaver or really old 3D Frog Frenzy. Stuff that's really old and needs some very specific tweaking that the general fixes can't fix. So you can go and play with these. I highly recommend it. There's some really funny things in there, but a lot of it's pretty generic. Like for WordPerfect, if you look at the source code leak for, I think it was Windows 95, and you can grep through for curse words or other things, you'll find that they had to resize the industry standard printer paper to fit WordPerfect's ideal version, or else it crashes and stuff like that. But a lot of these fixes are fixing very specific little bugs that the developers refused or couldn't fix anymore. Because apparently losing source code to your main product is like not unheard of. So a little caveat of using this program, you do have to be administrator, and I'll tell you the reason why in a minute and how we can get around that. And it is a public version. Microsoft has its own private internal version, which lets them use hot patching. This program, this public one, doesn't have any awareness of hot patches. So if you pull down a fix-it patch and you have that SDB file and you pop it in to the compatibility administrator, it won't have any like fix information in there because it's not aware of patches. And I'll talk about how we can use patches in a minute. So what actually happened when a shim was applied? Well, 2 registry entries were made. One under this custom folder where it says putty.exe, and that's how it knows how to trigger off a putty. And it has a GUID in there. It was just randomly generated, well, based off the SDB file, actually. And then under a folder right under that called installed SDB, there's that same GUID. And in there, we have this database path where it actually shows where our SDB file is. You remember I deleted the original one, but when I installed it, when SDB inst was executed, it actually created a copy and dropped it into this path of C:\windows /app-patch/custom. And we can see that here. This is the inject.dll putty, or the putty inject.dll SDB file that was on the desktop. A copy was just made and it was put into Windows, the Windows directory, so that people couldn't mess with it anymore. Lock down its permissions. And those are the registry keys, and those are the default file locations that'll drop things. Do we have any questions? I'm totally going to give a shirt to someone who has a question. Yes? You don't see the DLL? Like, where is it? The DLL, the path to the DLL is in the shim file, in the SDB file. So the DLL, so your question is, the DLL was on my system, right? Okay, so I was thinking about not mentioning this, but it doesn't have to be. You can actually specify a UNC path to have your DLL loaded remotely. Your DLL doesn't have to be local. Also, this path doesn't have to be local either. You can load a shim file from across a network with an UNC path. So you don't even have to have the malicious shim on the native system. Ask me for a shirt later. Yes? Yes, exactly the same way. It's all about compatibility, man. Yes? Can you detect shims by looking at API hooks? Yes, and I actually am releasing a tool that does exactly that. Moving on. So when you use SDB inst to install a shim database file, it'll add an entry in the add remove programs menu. And all the malware that I've seen that uses this will do this, which will use the SDB inst to install their shim. And remember when I said you only need to add those two, well, it only added those 2 registry keys. That's all you need to do. SDB inst does this extra for you. And you can make it look a little bit more like .NET framework update, blah, 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 supercritical, whatever. But if you just add those registry keys manually, you don't need to use SDB inst, and you don't need to have it make a little suspicious entry for you. I don't know why the bad guys still use SDB inst. And as a simple method of detection for SDB files, there's a little magic file header. Does anyone know what the ASCII string is there? If you do, I'll buy you a beer. So I'm just going to randomly give stuff out. I've got a cool little power adapter for my company. It's like international because my company's all global and stuff. What can we use Shims for? Hash, hash programs? Yes, persistence. This is a little heavy. Okay. Yes, persistence. That's the biggest and best thing. Super targeted persistence. And some cyber espionage groups have used this to target super specific SCADA software. And whenever that SCADA software runs, their program will run. If that computer never runs that software, they don't care, and their malicious code never gets executed. But we kind of already had that form of persistence with like this registry key, the image file execution options. If you have your program listed in there and you have a value of debugger and another value where you can specify another executable, some.exe, it'll run your debugger, your whatever that is, it doesn't actually have to be a debugger, instead of the original code. So we kind of already had that kind of form of persistence, but with Shims, we have a lot more flexibility, a lot more power. We can do like API logging. You saw that there was just a very simple fix for that, and it just chunks out a file, and it can also do, I think, name pipes. We can just kill any app. There's a fix called terminate exe, which just stops a file from running. Before the user code ever executes, it's like built into the Windows loader to do all this stuff. It just kills it before any DLLs even get loaded into the process space. It's not exactly true, but none of the users' DLLs, none of the third-party DLLs get loaded in. We can, since we're in the process space and we have lots of cool little shims, we can catch all the credentials that an app processes. We can redirect application logs. We can snoop and /redirect network traffic. We can Trojanize any application, as we saw with PuTTY. We can force old DLLs to be loaded. We can force vulnerable DLLs to be loaded. If I want Explorer.exe to be maliciously compatible with MS, blah, 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 068. What was it? It was MS-12 068? No, MS-08 067 was what I was thinking of. Anything you want. If you know where the DLL is that has that vulnerability, you can specify that that DLL should be loaded instead of whatever the current one is being loaded. Oh, that's not good. It's like dumb PowerPoint. Anyways, we can subvert / do anything we want system integrity wise. Like if you want to mess with the file integrity checker, the signature checker, you totally can. You can bypass UAC, and this is what bad guys have been using the application compatibility toolkit for, the ACT, for most recently, and I'll talk about that in just like the next slide. It was patched, but I'll talk about that. And since I'm a malware guy, I'm really big into malware obfuscation, and I'm going to show where I think this abuse of the ACT could go. So as part of a UAC bypass, Microsoft actually made this UAC bypass. They made this undocumented value in the manifest part of the file that says auto elevate true. And that file automatically gets elevated to administrator or system or whatever it needs. Because a lot of people in Vista were complaining that the UAC prompt was going off all the time because all these programs in the background needed to have access to the hardware or whatever else. So Microsoft was like, well, we can't just give this value to just any program. We'll only let our own programs use this property. And so they said, if it's not signed by Microsoft, this doesn't even matter. But if it is signed by Microsoft, then if auto elevate is set equal to true, it can go up to administrator or system or whatever it wants. It sounds like a legit reason, right? Operating system needs to do things and people can't be bothered. Well, funny, we have this fix called redirect exe. It takes in like two little parameters where one is your old program and one's your new program. And you say, okay, when this thing runs, say like sound volume, and it has to run with system, run my malware instead. So this is some malware that's totally doing exactly that. either Dridex or Dyer. I know one dropped the other, and they both got the code at the same time and started using it. And so the authors probably like shared that little tidbit. But this is how bad guys were really using and abusing the ACT. Oh, I forgot to mention, this patch here was just released a few months ago, and it was optional. And I know for a fact that there are lots and lots of people out there that did not install this. So technically it's patched, and really all it does is it removes the auto elevate value from SDB-inst, the installer for our shim database files. So now the installer won't automatically elevate, but like I said, who installs the optional patches anyway, especially like enterprise-wide? So malware has been using this for a while, and I wouldn't be talking about all these horrible things if I didn't already know that bad guys were already using this, and I'm just like, okay, well, we need better defense. We need to talk about this, and we can say, hey, I think this is going to go like this. This is how it can be abused even worse. I wouldn't just be like releasing lots and lots of attack tools or anything if bad guys weren't already on it. So the UAC bypass here in the green has been used by several malware families, and it's getting increasingly popular. But very recently, some malware families, particularly one called Gootkit, I think it's French-based. It's actually relatively like a really cool little piece of malware, but it started using the in-memory patching, where it was like, okay, Opera launches, hook all these functions, or Chrome launches, hook these functions, and that's starting to get super dangerous. The first malware family that I'm aware of that was used in the ACT was a malware family called Black Energy, particularly the second major iteration. And it's a pretty interesting family because it started out as cybercrime and DDoS and remote Trojan stuff, and then it started moving into cyber espionage. It got like 64-bit components and rootkit plugins, and it had SCADA system modules. Like it started getting pretty interesting, and the group started getting a lot more aggressive with its targeting. And it was actually outed last year by my company, iSight, and we called it Sandworm. And most people were just like, it has nothing to do with worms. And it's just like, actually, they had like this 0 day and this 0 day, and that's the thing you should have been paying attention to. But we actually named it that because a lot of like the C2 infrastructure and a lot of other things had a bunch of references to Dune. So they were like really all about Dune and sandworms. So we named them for that. They also did an interesting thing where they applied a fix called Disable NX Show UI, and that pretty much disabled / neutered DEP, or data execution prevention. So they were targeting a process and making it more vulnerable to exploitation, which I think is pretty interesting, among other things. The second group that I want to talk about is one called Roaming Tiger. It was outed by ESET's Anton Sheriponov. I'm sorry, Anton, if I butchered your name, at Zero Nights in 2014, last year. And here with a tool called SDB Explorer made by John Erickson, we can see that, well, this tool is actually really cool. I'll tell you more about it in a minute. It shows you all the little details, including the patch information for SDB files. And here, this group did something pretty interesting where they said, I don't want to use any of the fixes that Microsoft's provided me. I want to use my own fix with Blackjack and other things. No Futurama fans in here? Okay. So they said, I want the fix called acprotect_shim. And then right under that, you can actually specify in the SDB file format, you can specify a DLL where that fix is implemented. And they just specified their own DLL. So in essence, they have an inject DLL fix without using that particular fix. And I'm pretty sure they did this because they wanted to target both 64 and 32-bit programs, and the inject DLL fix only applies to 32-bit programs. They took that out for 64-bit processes. Sad day. So making a custom fix is actually pretty easy. We only need to export two functions in a DLL, and that's get hook APIs and notify shims. And if you're pretty good at reverse engineering, you might be able to figure out how GitHook's APIs works. And you can actually like say, oh, I want to hook this now. I want to hook all registry functions. I want to hook all, file system functions or whatever else. And then you just need to make an SDB file, a Shim database file that specifies that your DLL has the fix that you want. Does that make sense? Awesome. Thank you for nodding. So I also wanted to talk about how I prefer stealth and misdirection when I'm doing like red team stuff. And when I was at CCDC, I noticed some people were kind of just blatantly killing processes left and right. And I was just like, we can do shims for like every malicious action you're doing, we can use shims. And I started thinking, well, a lot of teams out there, a lot of cyber espionage, cyber crime teams, they already have malware. And they kind of like to stick to that and program their capabilities into that malware. So how will they probably use the ACT maliciously? And I have a bunch of anti-analysis, anti-reverse engineering type scenarios that we're going to walk through. But I really want to point out this idea of old to new, where I can drop like a 10-year-old Trojan on a machine, and some IR guy says, oh, we're getting weird traffic, and he goes to that machine and pulls off this executable. He's like, I don't know why the AV didn't pick this up, and he's like, oh, reverse engineering real quick. It has a hard-coded IP address. It's like a really old, crappy IRC bot, and I drop it into a sandbox and virus total, and it's like, yeah, it's 1,000,001 detections, and yeah, it goes out to that IP address, and he goes on, he like hands that IP address over to the hunt team or the SOC or whatever, and they go search across their enterprise for that indicator, and they don't find anything. So they get, great, don't know what that was, but whatever. In my scenario, there was a shim on that computer that every time that piece of malware ran, it would hot patch a new IP address into it. It would hot patch new capability into it. Like instead of going over IRC, it would just make an HTTP request. Instead of only being able to execute 3 commands, it could execute like 50. So we can use like the tactical capability of the shims to extend malware, to obfuscate it, to change it however we want, to change any process however we want. So I think that's pretty cool. So let's see if we can do these demos safely. Probably not, but whatever. So the first demo is I'm going to demo putty. Now you may be thinking, okay, well, we already did putty. Is there going to be a new fix? No, it's going to be inject DLL. However, I'm going to show you how we can use other people's tools with the shims. So I'm going to use putty to just SSH into a server just to prove to you this working and normal and good and nice and everything's happy in the world. And over on the right here, or left here, I have a Kali box set up. I'm just going to start a netcat listener. Oh, resolution is terrible. I'm sorry about that. All these demos are posted online, especially sdb.tools. That website has these demos as well. So I'm just going to start a netcat listener, and I'm going to spin up my application compatibility toolkit and do exactly what I did before, which is specify putty and go to inject DLL, and I'm going to specify this particular DLL that was made by Adrian Fortuna. I'm sorry, Adrian, if I butchered your name. And his putty writer DLL is what the program he made. When it's injected into putty, it will hook the input and output networking functionality. And it will create a connection out to whatever hard-coded IP address or whatever I wanted to, and it'll send all the data, like the input, the output, the keystrokes, everything, to my netcat listener right over here. And that's awesome. Not only that, you can also put in a command that'll run upon connecting to a new server, and it'll hide the output of that command from the user. Sound like fun? Yeah? Yeah? Come on, guys, I'm gonna start throwing things at you. So I'm just gonna use SDB-inst to manually install it once again, just to go through the motions, make sure that people know what's going on, not just using the GUI tools. So we can see as soon as we executed putty, the DLL was injected, the netcat listener was made, keystrokes are now being sent over, and even the password and clear text over here. And even The nice color control characters are being sent over too. So pretty cool. So if I was a bad guy, Putty Writer is definitely something I'd be friendly to. This next example, I'm going to take Firefox right there on the desktop, and I'm going to just start it and say, okay, this is Firefox. It's normal looking, normal acting, nothing's modified about it. And over on the right here, there's a Windows 7 machine with a share open called Catch, and this machine is called Controller. I'm going to redirect its profile, the Firefox profile, all of its internal files, I'm going to be sending over the network. So I'm going to select a fix, a really cool fix called correct file path. Now, the first thing I'm going to do to this fix under the parameters is /b or -b. -b means whatever you were going to do, don't do it. That may sound a little weird, but this fix was originally made for programs that had hard-coded C:/documents and settings, and you run it on a Windows 7 machine, it needs to redirect that to C:/users. Makes sense, right? It has like tons and tons of little file redirects. But -b says, don't do any of those. Instead, I find this Firefox profile, I copy that path, and I say, in quotes, that path, semicolon, the new path. So it's just old path, semicolon, new path. And I say //controller/catch. And that's this SMB, or this is, yeah, the SMB share that's open. And I'm just going to right click and say install. After saving the database, of course. You have to save the database before installing a shim, because it has to actually have a file to copy into the Windows custom directory. Which again, you don't have to do. If you're editing the registry directly, you can just specify whatever you want. So you can delete the original and start up Firefox. And as soon as we do, you can see all these files are being populated, are being sent across the network. And right there, key3.db, that's where Firefox passwords are stored. And we can see Firefox isn't complaining about any corrupted profile or the profile moving or anything. The operating system is lying to Firefox, and Firefox is just happy to go along with it. Isn't that awesome? Like, imagine what you can do when you have the power to say, yeah, that application has some really interesting logs. It would be awesome if I had all of those logs every time it starts. Yes, sir. Correct. So your question was, if I can repeat it properly, Firefox made all these new files because that old profile that we copied the path to, like when it started looking at that directory again, it thought it was starting for the first time and it doesn't have any passwords in here. And yeah, you're absolutely correct. And if I was a more thorough pen tester, I would copy over the whole profile first and then apply the shim so that not only do I have the passwords, but any new passwords as well. And actually, I'd probably be a little more devious. I would probably like instrument Firefox somehow and just get the passwords, not the, actually, you can redirect just this file instead of, going through the whole directory. Any other questions, comments, concerns? Cool. The last demo I wanted to do was, I was at CCDC and this gave me the idea for subverting the system integrity. Now this program called Autoruns, let's see if I can pause it. It says it's not even playing. Okay. So this program, Autoruns, made by Mark Rosinovich. I'm sorry, Mark, if I butchered your last name. It's part of sysinternals, and sysinternals is this awesome suite of programs, and they're really fantastic power tools. Autoruns here will show you the most comprehensive list of auto start locations in Windows for DLLs, for executables, all this other stuff. And it's great, I love it. And I saw a lot of people using it in the competition, and I was just like, you know what? I can mess with this. But I can't mess with this video. So here I just ran Autoruns, just to show you what's going on, and that it's like, not picking up anything crazy or malicious or anything. And then on the desktop here, I have this thing called POS Grabber. Now the Dexter source code, it was some POS malware, was publicly leaked a while ago, so I just downloaded, compiled it, and just put it on the desktop. No big deal. I'm executing it, it's going to delete itself. And now when we run autoruns, we're going to see that malicious key. Autoruns is really cool, especially the latest versions, where it will show you in red some really suspicious things, like unsigned executables, things named weird, things with no description. And there is, in the current version, run key in the registry. So I'm going to apply a fix. And it's one I made I didn't make in the demo, but I'm making it publicly available. I just made it beforehand. And I'm applying a bunch of fixes. So for autorun in particular, I'm rerouting registry keys. So it thinks it's going to, pause this for a second. It thinks it's checking one key, but I'm actually routing it to an empty key. So it's not going to see the malware. Isn't that awesome? I'm also going to just flat out use the terminate exe fix to just kill all of these other ones. Like proc dump, process explorer, procmon, ps kill, and a few others that I find annoying. And I also shimmed one other thing I'll show you in just a minute. So here I'm starting up all of the last 4 versions of autoruns, just to show you that each one of them is being shimmed, and none of them are showing the malicious autorun key. And that's normal. That's actually like built into Windows. This autoruns has a capital A, so it is not going to be shimmed. And there we have that malicious key. And you can right click and say, go to entry. But we don't see anything when it says, go to entry, and it pops up regedit, because regedit is being shimmed too. Because regedit can also be fixed, because it's going to also look in that same run key and not going to find anything. It's actually checking that 2 keys above where it says policies, where it's completely empty. All right. So that was a lot of fun at CCDC. They never found my malware. It was hiding under like the most common registry key ever. Did it fail? Oh, no. So I'm going to do this a slide forward and then go back, so we don't have to go through those videos again. Whoops. Okay. So we ran through how we can use third-party tools. We ran through how we can use specific fixes to do something really malicious. We ran through like subverting the system integrity, like I mentioned before. And if you just want straight up persistence, like a lot of people do when they first see this, you can shim explorer.exe. And I'll show you exactly how to do that here in a minute. But first I want to, let me see if I can run through these videos. Okay, awesome. But first, I want to talk about how we can use this with malware, in tandem with malware, and what I would like to call like maliciously compatible software. So I broke it into 3 broad categories. The first one, 10 minutes? Okay. Let me see. Okay. The first one being benign executables, where we have like putty.exe or whatever else, and we inject our own code and we make it malicious. And there's lots of different fixes we can do to accomplish this goal, like inject DLL or load library current working directory, and lots of other fun ones. If you think of good ideas, like feel free to tell me. I love hearing new ideas. My second category was dependently malicious executables, where we could have something that would normally just do nothing or would work just fine, but wouldn't have the malicious functionality appear unless the shim was installed, like some kind of kill switch, like the ignore exception fix. And there's a few other fixes, but the hot patching is actually, I think, the way more powerful. And the last part is an obfuscated executable, where it just will fail completely unless the shim is on there to correct whatever it's doing wrong. As a simple example, with MSF Venom, I just chunked out some shell code and I put it in this array, so this shell code array. And in my main function, I execute the shell code array. You got that? Right? But right before, I just have like one little line of assembly. And that is label, jump to label. This is an infinite loop. This will produce the EBFE instruction, like jump to self. So if you execute this thing, it just will hang there. Nothing will happen. If you put it into any sandbox, it won't say it's malicious because it didn't do anything. It didn't do anything, except for maybe if it scanned the shellcode and was just like, oh, that's malicious. But if we wanted to produce a shim that would just get rid of that one instruction, that EBFE, those 4 bytes, right? Is that 4 or 2? 2, sorry. Then we can just use John Erickson's SDB Explorer. As I mentioned earlier, not only can it look at SDB files, but can also create them. We can say at RVA 1000, just patch over those 2 bytes with 9090 with NOP. So it essentially just gets rid of that jump instruction. I mean, you can do lots and lots of really complicated stuff, like reroute all the jump instructions or jump into other and like have a jump into another instruction like some packers do. But this is just like a simple demo. Actually, 0x90 isn't NOP, it's exchange EAX if you check the Intel manual, just FYI. So if we wanted to make a shim to do this sort of thing, all we have to do is make a config file. You do sdbexplorer.exe/c for capital C for config, and then output our SDB file with a -o option, and then SDB-p to install an SDB file with a patch. So the last category is like malware obfuscation, I think has a lot of potential. There's a lot of stuff you can do with hot patching, right? So here, right under my main function, I'm going to XOR the first array against the second. I'm going to XOR shellcode versus shellcode key and save the result back into shellcode and try to execute it. Try to jump into it, whatever it is, right? So we can hot patch this key to be anything we want. We can control the output. Because they're the same length, we can control what it'll decrypt to. We can have it go to all NOPs, and if we have our SDB file over a UNC path or whatever, we can control when it becomes malicious. So I think that is super powerful. We can remotely control when something suddenly becomes malicious. And this is the config file to make it malicious. Any questions, comments, concerns? So this is a very simple persistence mechanism with just explorer.exe for Windows 7 32-bit, Windows 7 64-bit, and Windows 8 32-bit. And it'll just, with that shellcode, it'll just pop calc. So what can we do in terms of prevention? Well, we can disable shimming via group policy, but that is not recommended because Windows uses shims all the time. And especially, you wouldn't be able to use fix-it patches if there was a 0-day coming out. We could just delete the files, but that's even worse because you wouldn't just silently break things. You can remove the SDB instance installer that's on every Windows system out there, but that's not really effective. If you just write to the registry key, you can get the same results. And the tools that are already out there, the top 3 or the top 2 we talked about, like the Compatibility Administrator and the SDB inst program. Mandiant and FireEye made a shim cache parser and a shim cache memory scanner. That's a volatility plugin that just won a contest, by the way. But they check the cache because every program that's starting and executing has to check a cache of whether or not it needs to be shimmed. It's a good thing to cache, but it's also an excellent list of what has executed on that system. These last 3, they SDB Explorer and Python SDB are open source. Shims is not. They just display information about shims. But none of these help with like defending or preventing malicious shims. So I'm releasing a whole bunch of tools. I'm going to run through. I have to run through this real quick. Shim file scanner. You can just right-click on a file and say, "Will a shim be applied to this executable?" The shim process scanner scans all the processes on your system and tells you which ones are shimmed via undocumented application compatibility flags in the PEB and loaded DLLs. Let's see if the shim engine is actually even loaded. And a little script to do this. Shim guard, I was trying to make a program that prevented shims from even being installed. Right now it just alerts. Turns out permissions on registry, folders, and keys is like really hard to get right, or else you risk messing up a lot of stuff. And I made a little PowerShell script to do that as well. And then I made an autopsy module, for those of you who know what autopsy is. It's a forensics toolkit built on top of the sleuth kit, and that'll search for SDB files. And then I made a volatility plugin called SDB Scanner, and I'll do a pull request here in a minute, but it's on my GitHub right now. And it scans for shimmed processes on a machine that's been possibly compromised. I give Microsoft a lot of crap, and I'm going to show you a few of their awesome quotes here. But they honestly do a really awesome job. I love that it says, no shim is available to bypass the UAC, except for that redirect exe and the load library redirect. There's no limitation. This limitations by design. We are not allowing third parties to inject harmful code into the loading process, except for the inject DLL and the custom fixes. My favorite, you are not opening any additional security vulnerability. You cannot use shims to bypass any security mechanism present in Windows, except for the disable advanced RPC hardening client hardening, except for the disable Windows Defender fix, except for the disable ASLR fix, the disable SEH fix, the disable NX fix, the disable no signature check fix. There's more stuff in there. What you need to take away from this is that shims are easy to create, they're widely supported, and they can be super malicious. They are used in the wild right now by bad guys, by some really bad guys, and they're going to continue to be used because that's the super powerful stuff there. And incident responders need to be aware of how shims can interact with processes. They need to be aware that that benign file may not actually be benign, that executable, that Trojan may not actually be all that it is. All right, I don't think we have time for questions, but I will hang out here as long as I can / back to the room. Again, that's my Twitter and GitHub and all that other stuff. Is there anything I can help you all with? That's it, go away.